recording. All right, so thank you for joining me. We have been doing N64 assembly language, and we've been working on fonts. We need to be able to print text to the screen so that we can. It's just going to make debugging and lots of other things much, much easier. It's been a while since I left off, so when I left off, I was actually a bit stumped on the bug that I had, and that's not a good thing. I could sit and stare at the screen for an hour. I'm trying to do this all live so you can see the mistakes, but having me sit and stare at a bug for an hour was not going to be productive. I did work on this bug offline, and but I'm going to show everything I can about this bug so that you know all of the background and at least some of the steps that I went through. Probably some fewer of the dead ends that I went down, but you'll see the ones that were important and ones that just helped me get to where I needed to be. All right. So the first thing is we run it, and we're going to just see where we left off. What does the screen look like? Oh, okay. See, I forgot the command line that I created. It's been a while. Alright, so just loading up MAME with our last ROM, and oh, crumb. I am doing this in a virtual machine, and MAME is very resource intensive and tends to lock up the virtual machine when I let it. So we'll see if I can get some control back. All right, well, while this is opening, so we can kind of see this red with gray blob. The funny thing is that that's supposed to be the H in Hello World, and it's not. Not even close. It's not a solid color, but it's definitely not what we want. It doesn't look like any other characters. So we kind of have to figure that out. All right, so I did just manage to kill MAME, so I am back in control. Oh, okay. So I just need to type in debug in order to run it with debug instead of a normal run. All right. So this way we'll get our stepping debugger, and we'll be able to look at stuff when it goes wrong. Again, it defaults to the normal boot code, and this I call it 8000 1000. That is our first instruction that we have actually written, and I used a few nops to kind of break up the code. So here we have our init 16, which gives us our color, but crimson and silver, this is the color that we were seeing on our screen. So it's the red silver color, so it's the second line. We'll look at some more of this stuff in a moment. So I'm just gonna go to here. And I'm going to set a breakpoint. And there we go. So that's our character, but the rest of our session is still fully responsive. Yeah, that one's not right. So where do we look? If we go back to our code here, we really, first, I'm going to make this a little simpler, and I'm going to comment out those two sections so that we're dealing with just the simplest implementation that we can. And then I'm so make that, and we will run it again. I just hit F5 and it goes right to my code. So this first block is the video initialization section, and then here we have just a few lines, and they set up the A0, A1, and A2 parameters, which are those three parameters for this call to pixelate init16. And right after that, we set up A0, A1, A2, A3, and V1 for our static text. So the goal is that this is going to print hello world. So we're expecting that first character to be an uppercase H. And then this is our final loop. We can see the 8011 OC is actually pointing back to itself. So again, I'm just going to set that breakpoint and say that. All right, well, we have these two lines of code, the init and the text. The first step is, where is the problem? Is it in the first section or the second section? So, how I realized this when I looked at it, but I didn't necessarily initially go there. So what I'm going to do is I'm going to open a new memory window, and so let's see. The first is this address, the A020 5000. So that's a memory location, and that is it's going to take the 1-bit font, apply those two colors, and put it into this location in memory. So we're going to go look at that memory. Okay. So we can see that it's kind of a lot of random stuff. That seems okay. But it took me a while to realize that I should be able to so let's see, I'm going to back up a moment. My bit depth, my color depth is 16 bits, which is 4 characters here. So C630, and we can see that it's duplicated. And so what this kind of means is, for each pixel that we see on the screen, it's those 4 characters wide. So it's a little... So what we're going to see is, what we would hope to see is our letter H about double width. So you kind of like cross your eyes or squint at it funny, and we should be seeing some characters. And we're not. We're seeing all kinds of random stuff. We're still seeing the colors like we want, and they're the right length and all of those things. So it's kind of works, but it's not working. So let's let's take a little closer look here. So we can see that our first few characters are the punctuation characters, so those are kind of hard to tell visually. And again, if you look here and you kind of squint, you might be able to make out the character that's being represented. It's like this paren is fairly clear if your eye follows those ones. So we should be seeing something like that, only double wide in the memory viewer. But I'm going to go down to where our uppercase H is, which is right here. And so that should be really clear. Like, we can see that pretty well. I am going to... anything that I don't have to memorize, I don't. So the ASCII value for H, I'm just going to look it up at ASCIItable.com. Sorry, the screen kind of froze up. It'll come back in a moment. There we go. So the uppercase H is 72 in decimal. So we're going to do some math and kind of figure out where in memory that is. So 72 characters in. Now, I haven't done this math and just thought it through in a moment, but this is 8 bits times 8 rows, so that's 64 bits, which is actually 100 but our color depth is 16 bits. So I'm going to kind of do this rough in my head. 8. This is 8 bytes as it is, times 8 bits per byte is 64 bytes, times 2 because it's not 8-bit color depth, it's 16-bit color depth. So 128 bytes of data per character. So we're going to take the 72 times 128, and that is 9216. If we do it in hex, 24,500. And if we come back here, we have that 5,000. So we're going to add that. So we should find our uppercase H at A020 7400. So A020 7400. And this doesn't look anything like our H. So what this is all telling me, what this all boils down to, is that the problem is probably in the first section of our code. And again, it took me a long time to get here and to come to that conclusion. So we're pretty sure it's in the first section. Okay. And now that we know that, I'm going to set a breakpoint there, and I'm going to go ahead and do a soft reset. So if you do a hard reset, it will clear your breakpoints as well, because it's almost like a full restart of MAME. But a soft reset, I'll be able to just say go. All right. Oh, but it had some memory. You know what? We can find this really easy. I am going to hard reset, because I don't want to deal with leftover data in memory. It'll be harder to troubleshoot and actually debug what's going on. And it is thinking. right. All right, I'm going to go ahead and end it because we can restart real easy. All right, so we're going to go back to the debug on this. And so we're pretty sure this is in the pixel initialization, which is this first block of code. I'm going to actually set my breakpoint there, run, and then I'm going to do F11, which is to step in. We have the delay slot instruction, and so we need to step into that with the F11. And so that's just that's some error checking that we put in here. And this was where it was really tough. And so you're just sitting here and you're stepping through, and this loops forever and ever and ever. And here, I'm going to actually set a breakpoint there. I'm actually going to pull up the source code on this. And here. So we're in Pixel 8 and it's 16. So here we have our labels, so it's a little bit easier to read and maybe a little easier to follow. So this is where the store half is our writing out our 16-bit colors, and so our colors are all seem to be good. And so that's good. And then here is where we jump back up inside of our character, and that's at the branch on not equal, which is that one. All right, but we do need to watch our memory here. A0205123. And so we can kind of watch as it's populating this. This is one of the downsides and why it took me so long to find it, because these first couple of characters are really normal, really easy. The first one is a space, literally. So it should just be all solid, one color, and I think it actually is. So so we can kind of see our memory changing in the background here. I'm going to move it up a little. And our second character is an exclamation point. So this was the first one where I started to see something. Actually, once again, 128 bytes per character is 80. So where technically you can see here in hex it's 80, and so we're still writing in the 70 range here, so it'll be a few more steps until we start on that. Alright, so we're starting to write our background color, and this is our first non-background color, and 1 to the third pixel in, and so that's good. And so the third and fourth pixel in will get colored. And then it should go back to our background color. So everything seems okay at this point. Oh, but wait, right there, it stopped being okay, because those two positions should be the D88. What happened? And so I'm going to keep going because I'm going to come back to those. And so now we are at the A0 row, I believe. Oh, no. We got one more there at the 90 row. So now it's the A0, and we write the first one, and we write the second one. All right. So this is where it's going to get interesting, because once again, this is an exclamation point. So we are expecting that this little block should be the D88E value duplicated. So we look here, and T1, if it is less than 0, so we're going to look at T1, and it is C0C with a bunch of zeros. Okay, that seems a little bit odd. But the thing, and it took me a while to catch my eye, this T1 register is our entire character. That's one of the cool things about this 1-bit font. It is actually all of these bits in one thing. But what is wrong here is with this T1 is all of the F's. And so the top half is F, and this is sign extension. So the N64 has 64-bit registers. It has 64-bit instructions and 32-bit instructions. And for compatibility, the 32-bit instructions only use the lower to the right 32 bits, with the top, the bit 31, it's 0 based. If it's a 0, then the left side of that is all zeros. If it's a 1, the left side of that is all F, and that is the sign extension portion. And so this took me a very, very long time to find. So I am going to, there we go. So we're going to move on to the next character, which is this quote mark. But we're going to see what's going on really quickly. All right, so we are not done with that. This is the one that I want. There we go. All right, so we just hit our breakpoint here on the load instruction. It's going to take the address in T0, which is just happens to be the 801208, and it's going to read a double, which is 64 bits, which is our entire character in one pull, and it's going to load that into the T1 register, which is currently all zeros. So there we are. And there is our T1. And so we can see 28, 28. That is our so I think if I take this value here and flip my calculator into binary mode, and I paste that, and I convert to hex. I get 28. So this is definitely my quote character. And so those top two lines are identical. So this is our 2828. And that is now loaded. So we're going to proceed. And so once again, we're watching that 2828 value in the T1 register. And right there, it went weird. Why? What the heck just happened? All right, so why? That is the tough question. N64 dev, we are going to pull up our data sheet because it's that kind of an issue. So once again, it's just down here in the references, I guess about halfway down the page. I've clearly used this link before, and the instruction that we're focused on is SLL. And so what happened is it took our 2828 and just made the whole register 0. And we want to know why. So down here in chapter 16, this is the SLL register. The instructions are in alphabetical order. SLL is the shift left logical. So what we thought was happening was we were just going to shift it one bit to the left. But it wiped out our register, and we need to know why. All right, here is shift left logical. The contents of general purpose register RT are shifted left by SA bits. So we're reading here. RT is shifted by the SA bits, inserting zeros into the low order bits. And so that makes sense. So we're shifting one bit. We're taking the T1 value, shifting it to the left one bit, and putting it back into the T1 value. Seems pretty easy. All right. In the 64-bit mode, this is where we're actually operating. The value resulting from sign extending the shifted 32-bit value is stored as a result. If the shift value is 0, okay, so that doesn't apply. The low order is sign extended. This instruction can generate a 64-bit value that sign extends a 32-bit value. So, what happened? So, yeah. If we say 28, 28, and then all the rest are zeros. So this is what our bit pattern looks like. Once again, this is the Windows 7 calculator. It runs on Windows 10. You can refer to the previous video for that. Actually, we are 64-bit. So this is what we're dealing with. Okay, and so as I said, it's sign extends. So it's going to look at this bit, this 0, and it is going to make all of the bits that are in 32 to 63 identical to this bit, which is 0. And that is why it wiped out our T1 register. Okay. Well, we know why. Now, to fix it. So once again, this is the 32-bit instruction. So what we actually need here is the 64-bit instruction. And that one is, oops, trying to go through here a little quick. It's actually DSLL, which stands for a double shift left logical. And there we are. All right. This operation is defined for the V4300 operating in 64-bit mode and in 32-bit kernel mode. And so we are actually operating in 32-bit kernel mode. So DSLL, and so this one, the contents of general purpose register RT are shifted left by SA bits, in our case 1, inserting zeros into low order bits. The result is stored in general purpose register RD. So there's no exceptions, there's no extra little notes or comments about 32 or 64. It's just going to work. And so our fix for this bug is literally, so this was my two colors, a D. That's it. That is all we need. And so now I'm going to close all of that. I'm going to get a new version. I'm going to debug. And run. And I'm going to take a chance. Set my breakpoint there. That is my final eternity loop. And that almost looks like my letter H. If we look at it and if we count, we can actually see that this was another thing that I already I fixed as well. So our font is 8 lines by 8 pixels wide. The 8 pixels wide are clearly okay, but we're drawing one extra line. If we look at our font, once again going down to our uppercase H, we can see that the next line is actually the top letter of the I. And so you can see that it's in 1 pixel, just like the top of that I character. So this 8 needs to become a 7. And once again, we will close that, make it, debug it, run to our code, breakpoint on our looping instruction. Alright, well that was not the right answer. That is a C. I go into this a little too confident and see what happens. Okay. T3. See, one of the downsides to assembly is it can be hard to comment and to know what these different values really mean. And so I am kind of cheating here because once again I did solve this, and I thought I had it. I'm sorry, I'm a little looking up my fix. All right, well, it's not there. It's not that clear. So I got to figure this out. So one of the techniques with the bass assembler that I found to help with structuring the code so that it is a little bit easier to comment and to modify and do whatever else you're going to do with is this. So this is a scope keyword, and then the curly braces define the actual scope. So with that, you can come in and actually give your variables names. What a concept. And it can be a pretty big refactor, but the goal is to really help you. So let's just kind of take this piece by piece and see what we need to do. All right. So that's the letter C. All right, well, we already went back on that change. That was 7 to 8. Wow. A1, A2, font destination. You know what? I am going to start, and I am going to, so actually this needs to be a variable, and font address, A0, and I'm going to actually make this a constant. Once again, when I say constant, it actually just belongs inside of this scope. And I'm going to call it four-color, which it is. And do that. And constant back color, A2. All right. So, this is also a constant, and that is mem size, font mem size, and 0x2 F8. So I've changed just enough code. I'm gonna go ahead and compile. I don't need to debug every time, but I like to make sure that I'm gonna at least compile. Alright, so now I can take Notepad++ is great, highlights this. So I'm going to take this English name and replace those. So that is font address +2. So now we have the 4-color. Really only use the one place, that's fine. The back color is going to be the same kind of thing. There we go. Alright, and so T3. Add R0 94. I don't remember what. Oh. Okay. So 94 is, so here we have 0 to 128, or 127, which is 128 values, minus 32, which are the non-printable characters, so they do not have a font character. And that is 94. And then, or 96, and then we take off the delete, which is -1. And does it take off that starting null? So the delete character again is a non-visible, so that one is not represented. So constant total so this is actually font character count, and that 94. So I do have the tilde. I go from the space to the tilde. So again, just kind of renaming these magic values. So 63 is the number of. It's actually the loop count. Font character bits. It should be 64, but it's kind of self-maintaining. So we'll take this and replace that. Alright, so what else do we have here? Font character count goes into T3. Wow. It's surprising how complex this can get when it's no longer in your memory. So because we defined this scope variable, we don't need to prefix all of our labels like we were doing. So we can kind of clean this up too. So this is the exit, which is that label there. And just kind of checking through. All right. Pixel 8 start. Ah, it's down here. All right, so that is the start of the font. So this is Pixel 8 font start. And since I renamed those, I'm going to go ahead and do that, and we compile. Great. All right. So again, we've already scoped these labels, so I can shorten this to just that new character one. And so that one's down there. So that kind of cleans that up pretty nice, actually. But we still haven't fixed all of our little deals, so we're still looking. Sorry, thinking really hard here. Oh. All right, all right. Well, I've cleaned that up. I realized why I couldn't find that issue that I had. Silly me. So once again, just running it till we hit our code. I'm actually going down to my loop, and yeah. Wow, rather silly. So first of all, my H works great. The extra line, the mistake that I made is that it was not in the init code where my problem was. It's actually down here in where I try to actually write the text to the screen, And so I believe it is that number 8 which gets changed to a 7 in order to fix that extra line. So we're going to test that. And again, just scrolling through quick. There we are. There's our uppercase H. All right, all right. So I fixed up those 2 bugs. I am going to take just a little moment to stretch, and we will be back. And if we look at our program code here, right here we're expecting to use the red silver font on our frame buffer 1, and we want the hello world text. Well, it's multiple letters, and that part is not working. So as I said, we're going to take a little stretch. We're going to come back, and we are going to output multiple characters. There's something going on there. All right. Thank you.